In this video, I'm going to be showing that these four statements involving the parity of integers are equivalent statements. In other words, we have 6 biconditional statements to prove, which is pretty considerable amount of work. So we're trying to prove that n is even if and only if n plus 1 is odd. We're trying to prove that n is even if and only if 3n plus 1 is odd. We're trying to prove n is even if and only if 3n is even. Let's see, where are we at? We're trying to prove that n plus 1 is odd if and only if 3n plus 1 is odd. And then we're trying to prove n plus 1 is odd if and only if 3n is even. And then we're trying to prove also, finally, 3n plus 1 is odd if and only if 3n is even. So what's nice about all of this is instead of proving these 6 biconditional statements, which would amount to 12 conditional statements, we can just prove 1 implies 2. So what we're going to do is just prove these 4 implications. And if you read the discussion on page 88 and also refer to our rules of inference, you'll see that if we prove these 4 conditionals, we'll get these 12 conditionals as a result. And so the rule of inference we're going to use is P implies Q, Q implies R, so P implies R. So you'd apply this rule of inference over and over again, and eventually you get to all these 12 conditional statements by just proving these 4 conditional statements. So I'm just going to pick out a couple of them to do, I think, but let's just start with 1 implies 2. So we've got 4 conditional statements to prove. I'm going to start with 1 implies 2. So 1 implies 2 is just saying for all integers n, if n is even, then n plus 1 is odd. Okay? So this isn't too crazy. You probably know this in practice, right? But we want to prove it more concretely than just saying, you know, an odd follows an even, okay? We want to write that out in a way that is not debatable, okay? So let me try to sketch you a proof here, and then I'll write it up nice on another piece. So this is my scratch work to kind of talk you through the way that I'm going to prove this. So I notice here with my conditional statement that my conclusion is a bit more complicated than my hypothesis. That doesn't necessarily lend to a direct proof, but I think it's a good place to start because you're thinking, okay, I'm going to start with my easier, more simple expression and work my way to this more complicated expression. It's worth a try. So I'm going to try this with a direct proof, which means I'm going to start by assuming the hypothesis, and then I'm going to try to prove that the conclusion is true. So what I'm going to do is assume that n is even, and then I'm just, as always, right, whenever I make an assumption about parity of integers, I'm always going to be applying that definition of even and odd integers in a way. So it's worth a shot to see what that gives you. So if n is even, I know n equals 2k plus, oops, just 2 times some integer, right? K is an integer. If n is even. Okay, so now I have that. Now I'm trying to conclude something about n plus 1. So with this new representation of n, let's see what n plus 1 looks like. Well, n plus 1 then, if n is 2k, 2 times some integer, then n plus 1 equals 2k plus 1. Okay, so then this satisfies the definition of odd integer. This is 2 times some integer plus 1, so we know that n plus 1 is odd. Okay. So that's not too crazy. I think you probably know that, like I said, but we want to write it out so there's no debate here. So let me try to write this out and see if you can follow along with this more formal write-up. So that was my scratch work, and now I'm going to go into my formal write-up. And I'm going to set it up for my writer and let them know that not only am I trying to prove these 4 conditional statements, I'm really trying to show that all these statements are equivalent. So I'm going to set it up for my reader and say, let n be any integer and we wish to prove, not wish, that's will. We want to prove, or we will prove, how about, okay. We will prove the following statements are equivalent. And then I'll just list those 4 statements that we talked about. So first one was n is even. The second one, n plus 1 is odd. The third one was, let's see, I don't think I remember the third one. Third one, 3n plus 1 is odd. And then the last one was 4, was 3n is even. Okay. And I'm going to set up the conditional statements that I will go through and prove, just so that my reader knows where I'm going and why I'm going there. So, I'm just going to say, to show these statements are equivalent, I will prove, we will prove, right? We will prove the following conditional statements. I'm just going to label them so that my reader can kind of follow along and not have just a big, section of text to try to piece together, okay? It can be, try to break it up into pieces a little bit. So the first statement, right, we're going to, 1 implies 2. If n is even, then n plus 1 is odd. Okay, the second one, if n is even, then, let me make sure I don't mess this up here. 2 implies 3, sorry. If n plus 1 is odd, then 3, which was 3n plus 1 is odd. Okay. The third one, if 3 implies 4, so if 3n plus 1 is odd, then 3n is even. Okay. And fourth one, 4 implies 1, if 3n is even, then n is even. Okay. All right, so the first one, let me write that one up quick because that might be the most straightforward one here in the bunch. So I'll do that one and then I'll do a couple more for you guys, okay? So number 1, assume n is even. Then, by definition of even integers, n is equal to, n is equal to 2k for some integer k. Okay, now we want to try to conclude something about n plus 1, so let's see how we can write out n plus 1. So I'm going to say, notice n plus 1 is equal to 2k plus 1. So, by definition of odd integers, n plus 1 is odd. Okay, so that finished the proof of 1. So now let's prove that second conditional statement. So I'm going to go back to the drawing board, make sure that I can get a sketch going here of this statement here. So I want to try to prove if n plus 1 is odd, then 3n plus 1 is odd. Okay, let's see. So I'm trying to think through here if I want to do a direct proof or if I want to try to do proof by contraposition or proof by contradiction. So let me just do some sketching here and let's see what happens with a direct proof. So with a direct proof, we'd start by assuming that n+1 is odd. Oh yeah, I see it now. This is going to work. So if we assume that n+1 is odd, then we can write out n+1 as 2k plus 1. Okay, so 2 times some integer plus 1. Now, we want to conclude something about 3n plus 1. So, if I can solve this equation for n, plug in that expression for n here, I'll be able to write it out as an odd integer. So let me show you what I'm talking about. So what I see here is, yeah, I've got this n+1, but now I've got an equation. I can work on both sides of that equation. So what I can say is, okay, we'll just subtract 1 from both sides, and then that will give me that n is equal to 2k. Okay? So basically what we're using here is that if n+1 is odd, then n is even, okay? Expression in our conclusion. So then I'll have 3 times 2k plus 1. So remember, if I'm trying to show something is odd, I want to show it's 2 times some integer, right? It can be a whole expression plus 1, right? So all I need to do is show that I can rewrite this as 2 times some integer plus 1, right? Well, 3k is an integer, so I've done that, right? I've shown that and 3n plus 1 can be written as 2 times some integer plus 1. Okay, great. So let's write that piece up. Okay, so we're going to start by assuming n+1 is odd. Then n+1 is equal to 2k plus 1 for some integer k. If n+1 equals 2k plus 1, then n equals 2k, right? Okay. Note, 3n plus 1 is equal to 3 times 2k, so I'm just substitution here, plus 1, which is equal to 2 times some integer plus 1. Because 3n plus 1 can be written as 2 times some integer 3k, 3n plus 1 is odd by definition of odd integers. Okay, we're halfway there. So let's just come back in the next video and I'll do those other 2 implications, okay? Oh, not quite done, right? Not ready. Unless I did some little lemmas here, right? These are my little lemmas, maybe. Okay.